Hello friends, I welcome you in lecture number 14 on series solutions of differential equations. From last 3 lectures we are discussing Frobenius method for finding the series solution near regular singular point, and we have seen two cases of Frobenius method in previous 2 lectures, and those cases depend on the roots of indicial equation. We denote the roots of indicial equation by R1 and R2, and we know different possibilities for these roots R1 and R2. First case was R1 minus R2 is not an integer, is not equal to an integer. Second case was we have equal values of R1 and R2, and third case is R1 and R2 differ by an integer, that is their difference is some integer. We have seen earlier two cases in previous 2 lectures, and today we are going to discuss this last case, that roots of indicial equation differ by an integer. And we know that if we have regular singular point, suppose x equal to 0 is a regular singular point of given differential equation, then at least one solution is always in this form: sigma an x raised to n plus r, n equal to 0 to infinity. And in this case, in third case, we will obtain the second solution by the method of reduction of order. In case 2 also, we have obtained first solution by using this form, and we have obtained the second solution using reduction of order. And here also we will first find out the first solution in this form, and using that first solution we are going to decide second solution using this formula of method of reduction of order, which is y2 equal to y1 times e to the power minus integral of p with respect to x divided by square of first solution and integral of this whole quantity with respect to x. So first we try to show that x equal to 0 is a regular singular point of this differential equation. Here it is not specified that about which point we have to decide series solution, but we are considering series solutions near x equal to 0 only in our course. So here also we will first show that x equal to 0 is a regular singular point of this equation, and then we will apply Frobenius method to obtain its solution. I have written this equation and I have given it number 1, and first I have to divide by coefficient of y double dash. So equation 1 is divided by x square minus x, and we have y double dash minus x divided by x square minus x times y dash plus 1 divided by x square minus x into y equal to 0. This I can rewrite as x times x minus 1. So this x will get cancelled with this x, and we will have this px equal to minus 1 over x minus 1. We are comparing this equation with standard form, and we find px equal to minus x over x square minus x, and from numerator and denominator by cancelling x we have this form of px minus 1 divided by x minus 1, and this quantity is qx. Qx is 1 over x square minus x, and then we multiply px by x and qx by x square. Therefore x times px equal to minus x over x minus 1, x square times qx equal to x square over x square minus x, and here x can be taken common, and that x will cancel 1x from this x square, and we have x over x minus 1. X into px is minus x over x minus 1, and x square into qx is x over x minus 1, and both are analytic at every point except x equal to 1, where this denominator becomes 0. Therefore x into px and x square into qx both are analytic at x equal to 0, and therefore by the definition x equal to 0 is a regular singular point of given equation, and therefore by Frobenius method we can say that there exists at least one solution of given equation which can be represented in this form: y equal to sigma an x to the power n plus r, with the assumption that a0 is non-zero, and y dash will be equal to derivative of an x raised to n plus r, which is an n plus r x raised to n plus r minus 1. Index will be as it is, n equal to 0 to infinity, and y double dash is sigma n equal to 0 to infinity n plus r an as it is. Derivative of x raised to n plus r minus 1 is n plus r minus 1 times x raised to n plus r minus 2, and once we obtain derivatives of y, we substitute y dash and y double dash in this equation. So I have written it x square minus x into value of y double dash minus x into y dash plus y equal to 0. In the next step we multiply this x square with this summation and minus x with this summation. If I multiply with x square is independent of n, so that can be taken inside the summation and it will combine with this power of x, and we have x raised to n plus r minus 2 plus 2, and we will have x raised to n plus r. So that is this summation minus this quantity into x raised to n plus r minus 2. Here power is 1, so we will have x raised to n plus r minus 2 plus 1, that will give us x raised to n plus r minus 1. Rest of the things as it is. Here also we multiply by x, and here I have x raised to n plus r minus 1 into x raised to 1, that will give me x raised to n plus r, and this quantity as it is, and this is as it is equal to 0. Now in each summation you can see we have x raised to n plus r in all these three summations, but here we have x raised to n plus r minus 1. So as usual, first we have to convert this power in terms of x raised to n plus r. So for that, this n minus 1 will be considered as new index, say m, and therefore n will be equal to m plus 1. When n will start from 0, m will start from minus 1, and here n will be replaced by m plus 1, so we will have m plus r plus 1. Here n will be replaced by m plus 1 plus r minus 1, so m plus r. This n will be replaced by m plus 1, and here n minus 1 will be replaced by m, so we have x raised to m plus r. So that I have written here, and rest of the things as it is. So there is a change in this summation, only these three summations I have written as it is. Now here in all these summations index is n, and here index is m, and we know that this summation index is a dummy index, so we can again replace this m by n. In the next step I have rewritten this summation. Instead of m I am using n again as the index of summation, so I have written that term here. Rest of the things as it is. Now to combine all these summations, we must take care that range of each summation is same. Here range is starting from minus 1. So what we can do is, we can write down the term corresponding to n equal to minus 1 and plus sigma n equal to 0 to infinity, this quantity as it is. So for n equal to minus 1, you can see if I take n equal to minus 1, this minus 1 plus 1 0, and I will have r, minus sign is there, so here also we will have minus sign. for n equal to 0, n equal to minus 1, we have r minus 1, and for n equal to minus 1, I will have a0 x raised to r minus 1 minus sigma times this quantity, but from n equal to 0 to infinity, and here I have negative sign, so I will have negative quantity here, and rest of the things as it is. So I have modified that summation as term corresponding to n equal to minus 1 plus sigma n equal to 0 to infinity, and due to negative sign here, we have negative sign at both of these places. Now after this, we write down this term first, coefficient of x raised to r minus 1, and rest of the summations can be combined now because we have index of summation is same, n equal to 0 to infinity. We can take x raised to n plus r common also, and I have written all these things here. You can see this is n plus r minus 1 into an, that is here, and then this quantity n plus r plus 1, n plus r, an plus 1, and after that minus n plus r an plus an, and x raised to n plus r common equal to 0. Now here coefficient of x raised to r minus 1 is this quantity, and this quantity is coefficient of x raised to n plus r. So first we compare coefficient of x raised to r minus 1 to write down the indicial equation. So because we have 0 on the right hand side, this equality holds if and only if coefficients of x raised to r minus 1 and x raised to n plus r are 0. That means we must have minus r minus 1 a0 equal to 0 and this bracket equal to 0. First I have compared coefficients of x raised to r minus 1, and I find that minus r minus 1 a0 equal to 0, and we have assumed that a0 is non-zero, therefore r into r minus 1 equal to 0, and this gives me r equal to 0 and 1 as roots of indicial equation, and we can see the difference 0 minus 1 is minus 1 and it is an integer. So this means we have roots of indicial equation which differs by an integer. So this is the third case. Now in the next step we equate coefficient of x raised to n plus r to 0. So I have written this quantity equal to 0 here, and the summation is starting from 0 to infinity, therefore we have n greater than or equal to 0. Now in the next step we can take an common, or we can take n plus r common first. So I have done all those things here. I have written the terms with an simultaneously, and this is taken on the right hand side, so it is here. In the next step I have taken n plus r common, and an is common in every term, so it is outside the bracket. From these two n plus r common, so we have n, or first I have taken an common only, so n plus r minus 1 minus n plus r plus 1 an equal to right hand side, and in the next step I have taken n plus r common, and I have n plus r minus 1 here, and here I have minus 1 plus 1 an equal to this quantity as it is, and this will give me n plus r minus 2 plus 1 an equal to this quantity, and from this I can write an plus 1 equal to this quantity divided by this quantity times an, and this is given as number 2. This is the recurrence relation. Now we have roots of indicial equation 0 and 1 which differ by an integer. So first solution we will obtain corresponding to the larger value of r. So here we have two values of r, 0 and 1, and 1 is greater than 0. So 1 is the larger root of indicial equation, and remember in this case we will find out the first solution corresponding to the larger root of indicial equation. So now we obtain we consider r equal to 1, and using r equal to 1 we obtain the first solution of given equation. In the next step, I have taken r equal to 1 in this recurrence relation. First solution, and taking r equal to 1 in this equation, we have an plus 1 equal to r is 1, that is n plus 1 plus r is 1, so this is 1 minus 2 minus 1, and we have n minus 1 plus 1. Here r is 1, so n plus 1 plus 1, that is n plus 2, and into n plus 1. If I combine these two, I will have n square minus 1, and plus 1 is there, rest of the things as it is. So this 1 will get cancelled, and we have n square divided by n plus 1 into n plus 2 an. This is the recurrence relation for r equal to 1. Now we can decide few of the coefficients by taking particular values of n. If I take n equal to 0, I will have a1 equal to 0 square divided by 1 into 2 into a0, and a0 is non-zero, that means a1 equal to 0. For n equal to 0, we have a1 equal to 0. If we take n equal to 1, here we have a2 equal to something into a1, but a1 is 0, therefore a2 is also 0. Similarly, for n equal to 2, we have a3 equal to something into a2, but a2 is 0, therefore a3 is 0. So in general, we will get an equal to 0 starting with n greater than or equal to 1. So I have written here, in general, an equal to 0, n equal to 1 to 3, and so on. So we have only one non-zero coefficient, which is a0, and hence the first solution is y equal to sigma an x raised to n plus r, and we are writing the solution corresponding to r equal to 1. Therefore we have sigma an x raised to n plus 1. This I can rewrite as, if I take n equal to 0, I have a0 into x, plus for n equal to 1, a1 into x square, for n equal to 2, a2 into x cube, and so on. But we have a1, a2, a3, all these constants are 0. Therefore first solution we will denote by y1 is equal to a0 into x. This is the first solution. Now this a0 is arbitrary, so we can consider any value for a0. I have taken a0 equal to 1. Since a0 is arbitrary, we can set a0 equal to 1, and therefore the first solution is y1 equal to x. So you can see here we have roots of indicial equations, indicial equation differing by an integer, and first I take r equal to 1 and I find the first solution, which is y1 equal to x. Now for second solution, I am going to use method of reduction of order. So for that we require first solution, which is x. Px we have obtained in previous discussion by comparing with standard form. We have written that p of x is nothing but minus 1 over x minus 1. I will require px in the formula of reduction of order to obtain second solution. So that I have written here, and I have ready-made formula for the second solution using method of reduction order. Here I substitute value of px. Px is negative, so this negative will be positive. Y1 is x, so I have written y1 also. E raised to minus of minus 1 over x minus 1, that is minus plus. Integral of this is log of x minus 1, and we know that e to the power ln alpha is alpha because these two functions are inverses of each other. So I have x minus 1 over x square. This I can rewrite as x over x square, that is 1 by x, minus 1 by x square, that is x raised to minus 2. Now integral of 1 by x is log x, integral of x raised to minus 2 is x raised to minus 2 plus 1 over minus 2 plus 1, and then we multiply with, before multiplying we rewrite this as ln x minus minus plus x raised to minus 1 is 1 by x, and if I multiply by x I have x times log x plus 1. This is the second solution. First solution was y1 equal to x, and we can observe that both are linearly independent. We cannot write y1 as constant multiple of y2, or we cannot write y2 as constant multiple of y1. Therefore y1 and y2 are linearly independent, and once we have two linearly independent for second order homogeneous equation, the general solution can be written by taking their linear combination, that is c1 into y1 plus c2 into y2, and y1 is x, y2 is x into log x plus 1, where c1 and c2 are arbitrary constants. So you can observe that if we have equal roots of indicial equation, that was second case, and if we have roots of indicial equation differing by an integer, then what we have done is we have obtained the first solution using Frobenius method. We assume that first solution is always in this form, and to obtain second solution we have used method of reduction of order, but be careful that it is not always easy to evaluate this integral. Here we have two integrals. First we are integrating p, and then we are integrating this quantity with respect to x. So this is possible if we can express our first solution in some closed form, or if it is comfortable or easy to find out integral, then only we can apply method of reduction of order. If it is not possible to find out second solution using this integral, or we can say that sometimes it is not possible to evaluate this integral, then we have to think for another criteria to decide the second solution in case of r1 equal to r2 and r1 and r2 differing by an integer. So that we will discuss in later as we proceed further. And this is all about this session. I hope you like it. Thanks for watching.